Now we will begin with our research panel session. So just to remind people, so this session won't be recorded. So we hope we can hear the most honest answer and also criticism from all the panelists. Okay, so to begin with, like following the title of the workshop, in your opinion, to what extent should inductive bias be built into the model architecture versus learning from that, from like experience, and why? So if you have an answer already, then you can just unmute yourself and then start talking. So what kind of inductive bias do you think we should build in the model, and what kind of inductive bias we should just learn from data?
Well, I guess I would say, in cases where, it's really clear that that property holds, like if there's some symmetry or something that is really well motivated, then I think, it's kind of clear you should do it. You should do it. And there are lots of examples that are coming up now, certainly with molecules and things like that, where it helps. One thing that we should be a little bit careful of is that sometimes there's a symmetry, like nature maybe has some symmetry, but that symmetry might not be respected in the data that we observe because you have measurement errors and things like that. And so in those cases, we should be careful to not put in the inductive bias because we have a mental picture that the underlying truth is nice and say symmetric, but if the data doesn't respect that as well, then we probably shouldn't. So so there's a little bit of a dividing line there, but yeah, I think there are many other cases where you can make where you can make an argument for doing it, but I think certainly in the cases where it's clear that it's there and you know how to do it, it's hard to imagine a reason not to.
Yeah, I think it's a little bit maybe contradicting to some of the speaker who mentioned like using like physics engine, which have like physics rule that is encoded into the physics engine. So I just wonder what is people's opinion regarding like, we know F equals MA, so we should write that into our system, or we shouldn't write it, and that should derive from the experience. Yeah, Kelsey, go ahead.
Yeah, I think this very much depends on what your goal is, right? Because, for example, if you wanted to, for example, the kinds of stuff Tomer and I do in modeling adult humans and the ways that they behave, then like building in an intuitive physics type engine makes a lot of sense because our goal is to explain that behavior, understand the behavior. But if your goal is to do something like discover a conservation law or something in a physical system where it's not obvious that that can be described by like, it's not even obvious that we have good enough simulators to be able to do that successfully, then you probably do want to be able to learn that from your data. And I think more generally, like I was quite compelled by some points that Kyle raised in his talk about the importance of picking inductive biases that you really want to be true in the generalization cases that you care about, right? So like, if it's very important that something generalizes to different numbers of objects, then like baking that into your model architecture is a very useful thing to do. And you can get certain guarantees out of that you couldn't get if you were to just apply a giant transformer or something to the data. But a giant transformer might naturally do something like coarsening, right? And maybe there's something to learn from that. And so I think you can't ask this question in a way that is divorced from what you want to use the resulting system to do.
Do other people want to add something to this? Nels? Yeah.
Right, yeah. I just thought it's definitely attractive to just model from data, to not impose priors and purely focus on the data-driven paradigm. But a bit what was also mentioned before, in many cases, I think it makes sense to be pragmatic. Say in fluid mechanics, I think we have really hard problems, and in a way we can use all the help we can get. So if we have equations that describe at least part of the problem, that get us part of the way to getting a good answer, I'm totally in favor of using that. So, right, unless it's shooting over the goal, if it prevents us from finding the right solutions, then it's definitely not a good idea. But in general, I'm a big fan of imposing such priors.
Okay, Tom, I see your reason.
If I could just, I'd mainly agree with Kelsey. I think it depends on what it is that you're trying to achieve exactly, of course, on what you're trying to explain, what the system is. And I mainly just agree with Kelsey's point. I will say it's a bit funny because you're asking a normative question, right? You're saying, let's sit and sort of think like, what sort of things should we build in? But in many ways, it's an empirical question. It's kind of funny because I see myself more as a normative nativist type person. But it's an empirical question. We try stuff and we see, like we try learning stuff from data and it doesn't really work. And it's hard to bet against deep learning and learning everything from scratch and things like that. I will say that looking over the last 12 years or things like that of trying to apply deep learning to human-like models to capture intuitive physics. Again, I'm trying to like really build a fence around a small area. This isn't meant to apply very broadly. One way of reading that is a triumphalist thing, like we're going from strength to strength. But another way of reading it is like, look, 12 years ago, you said you could do this with a convolutional bottom-up neural network. And ever since then, it's been like the cognitive revolution on steroids. Well, what we need is, we need a neural Turing machine, we need attention, we need memory, and now it's kind of like, well, we need objects to do this kind of common sense reasoning. So yeah, okay, fine, we need objects. The question is now, how do we build in objects? And people have different answers to that. I suspect something similar will be happening with agents. But I mean, sorry, one tiny other addition to that is that our sense is that evolution has built this in, and evolution is probably doing this for normative reasons. You don't want every child to have to rediscover things like objects and agents, right? We don't want to run this giant search over all possible programs to figure out something like objects. So presumably that's why we have something like core knowledge, is an argument for maybe building something like that in. But what exactly it is and how do we build it in turns out to still be an empirical question.
Great. I see Karen just joined. So Karen, now we are talking about to what extent should we build in the inductive bias versus learning it from data. Yeah. I see Shriran is raising the hand, so maybe you can go next.
Yeah, I think I agree with everybody you said. And I think one additional thing I want to kind of add to this question is, I think the original question is that what kind of inductive bias or bias we want to add to our model. I think apart from that, thinking about that question, I think it's also kind of important as a first step just to understand what already is built in our current network architecture. So it depends on what network architecture you choose. For example, if you choose ConvNet, convolutional neural network, you use convolutional operations that actually already has some inductive bias built in, like it's shared kernels, it has translational invariance. If you use pooling, it encourages invariance, right? So I think as a first step is actually kind of have a good idea of what we already built in, and then think about what are the other things we want to add. Hopefully things that is easy to add and also is correct and it helps learning. Yeah, so that's what I want to say.
Karen, do you want to add something to this question?
I'm worried that since I joined late, probably a lot of points being made. And if I repeat anyone, just stop me. The way I think about problem usually is the reverse direction. I would think about, here is my model, here's my physics, differential equations. Where can I inject data, right? It's like, I don't start things with the neural network. I just start with some differential equations and then, figure out a way to make it more expressive and reflect the real world better. And oftentimes, if this is the direction you go, how you approach your problems, then I think the problem is kind of natural, right? We start off from everything is biased to this model, and then we're going to relax different parts of this model and to make it more data driven. I think it's important to acknowledge that this is one possible direction to go, and then you can go from the reverse direction, start with neural network, and it's important to know that they could coexist, right? It doesn't need to be so for one example, it's like, if this is a component like contact, I talk a lot about contact today. I want to learn that from the real world data, and then that part, the learning components inside, could be you could also inject inductive bias in there as well. So for example, you can learn a neural network that actually satisfies some differential equations. So I think they can coexist, whichever direction you would like to approach.
Kyle, you want to add something to this?
I was just thinking that as we were talking that, there's another version of what are good examples of when you would not want to, even if you, certainly in the case where you're wanting to test if some symmetry exists or not, you can't assume it's there, because that would sort of beg the question. But but in cases where maybe you are quite sure that some property, exists, and you know how to implement that inductive bias, like when would you not want to? And I guess I can think of potentially two examples there. One is just in principle, it could exist, but I don't have great examples of it, which is that, we see a lot of the success of deep learning in the context of these very over-parameterized models. So they include, a solution that's what you want, but they have many other things available to them. And part of that has to do with the learning dynamics. And I do wonder sometimes if even imposing an inductive bias that's the right inductive bias, when that interferes with the learning dynamics. And I don't have great examples of that, but I imagine they're out there. And I think it would be interesting to have some sharp examples, so where it hurts. And then the other thing is that if you're in a situation where you have some mechanistic model, like our simulators are mechanistic models, and they have the inductive bias that we think they should have, but they're very difficult to work with. So there are other times where you just don't want to include it just because it's too detailed, right? So kind of for computational reasons. So I think we could probably come up with many other examples of where, even if it's well motivated, you wouldn't want to include it. And maybe it's interesting to think of it that way as well.
Yeah, and just to follow up, I find out like many of the panelists mentioned like defining the task is kind of important. So what is our goal? So I just wonder what's people's opinion regarding whether we want to build a system that is like human-like, at least like adult-like, or our main goal should be setting to build like AGI or superhuman models. And in which scenarios or in which cases do you think this make more like one of the other is better?
I can say something. Well, certainly, I think that these kinds of this framing comes up a lot, and I think you almost always see that you can be superhuman in one respect and totally not in the other. So it's very so we're already have many examples where we're using machine learning to do things that where human intuition has a shortcoming in the scientific setting, and it helps, right? To me, I think what's really interesting is just to try to think about how is it that, like, when I think as a physicist, how is it that physicists have succeeded in learning as much as they have about the world with basically very little computation and in some sense very little interaction with the in terms of experiments, and how can you use that as a guide for something that looks more like AGI-ish, whatever that means, but I don't think, to me, it's just a guiding post. It's kind of complementary to what you see in cognitive science. It's a very similar questions, but sort of grounded in a slightly different way with a slightly different focus.
There's an obvious argument for why not both, which is kind of the cowardly way, right? I will say this was a question also brought up by Urge. There's obvious reasons for building superhuman physical reasoners and things like that, and I think that's also what 90% of science and engineering, things like that deals with this, is trying to do, right? And various things. I don't want my plane to reason intuitively about science, right? I don't want my car to reason intuitively about a lot of stuff. So there's all sorts of like lots and lots and lots of focus in engineering and physics, and lots of headway has been made over like 200 years of trying to predict stuff in ways that humans are just really bad at. I think that's good, and that's how it should be. And that's where a lot of the focus should absolutely be. Landing lunar modules should not rely on my intuitive understanding of orbital mechanics. The question is there any reason to build something that's human-like? One, I think obviously just scientific understanding, right? I think human intuitive physics is fascinating, and if we want to understand it, there's a reason for building scientific models of that understanding. The other maybe non-obvious thing is taking a page from Liz Spilkey, which is if we want machines to interact with people, they will need to understand people's intuitive physics, right? To predict what people are going to do and things like that. So by virtue of that, they'll need to have a model of people's intuitive physics. Same thing for intuitive psychology, by the way. But I think a third and more maybe deep reason, which is kind of speculative, is that a lot of our later intuitions, a lot of our common sense intuitions about how the world works at a more abstract level, right? The way we think about, hey, listen, physics is made up of three things, basically, right? Energy, momentum, forces. I'm just spinning out stuff. You're already creating three objects in your mind and the relationships between them and things like that. There's arguments being made in development and cognitive science that a lot of those later common sense reasonings are inheriting from an understanding of physics, of objects and their locations in spaces and spatial reasoning and things like that. So if we understand those better, I think we'll be able to build on those as a basis for more common sense reasoning that we do want to build into machines.
Great. Karen, I think maybe you can go next.
Yeah, I just, Tomer has really good answers. I'm just gonna add a couple more. I kind of agree that if there is a choice between human-like or superhuman, I always choose superhuman. Why would anyone be, less than what you could achieve, the most optimal possible, setting? And I think the reason is just because we couldn't get it, or at least the current speculation is that we don't understand the world enough to build a superhuman models that could predict the world perfectly. But if we could, and if we have the computation and we could do this real time, I would always choose that. And I think the like other points that Tomer made was excellent. There, if we want machine understand humans, then that might be a reason that you want something. We first need to understand ourselves first, and so that's that. But then I think another difficulty of building this superhuman model for prediction is because it also requires really good sensing capability, right? Like right now, you need this model to be built first. That's hard, and then you need this model to be updated based on the current observation. And that is also, and that requires really, really good ability to sense the world and system identification and all that. So it's just a very challenging task. But if it could be done, I think it would just unlock a lot of possibilities for machines.
Okay, Kelsey, maybe you can go next.
Yeah, just to add, I mean, I agree with all the points that have already been made. And one thing I think that's maybe like underappreciated even in cognitive science is that there's a lot of work doing things like comparative cognition, right? And looking at comparisons between humans and other animals in the kinds of things that they can do and the kinds of intelligence they have, right? Like there are birds with far better eyesight than humans, and this enables like unique capabilities to birds relative to humans. Or there are like spiders that can do all kinds of crazy sensing so that they can jump extremely precisely, right? So different organisms are adapted specifically for their ecological niches to be able to accomplish the tasks that are most relevant for them. And I think there's an interesting question, even if we all agree that superhuman is really what we would ultimately like, there's this notion that you could have superhuman that's sort of a vector that goes along human but extends further, right? Or you could have superhuman in a vector that's totally orthogonal to human-like intelligence at all, but in some sense is able to come up with like very different kinds of solutions to humans, or like operates in a completely different way. And I think that at least one of the reasons why we study humans is because we think it might be easier to get to superhuman intelligence by going in the same vector direction as current humans than it is to go in sort of some completely orthogonal direction. But that doesn't mean that you couldn't also try that. And that's how I think like a lot of these giant transformer models are essentially saying, oh, let's forget about the direction, right? And just see what happens and try to get the best performance we possibly can.
Great. Sure.
Yeah, actually, yeah, I have very little to add. Actually, I raised my hand, but I feel that's most of my point already made. But I think I have one small thing to add. I feel in robotics, actually, we think about this question a lot, right? Like whether we want to build robots kind of like human or superhuman. And I think because our current robot hardware is so different from like the hardware that human has, so a lot of times it's not really like an option that's really kind of like built exactly like human, I think. But also I think sometimes like by thinking about building human like robots, sometimes maybe a little misleading in terms of a goal. I think oftentimes we want the robot to be able to be helpful, able to do some task, and it doesn't really need to go the route of how humans do the task. So I think thinking that way, so for example, like washing machine is not like how we wash clothes every day. So I think thinking that way also maybe can help us to think whether we define a task or define the kind of desired properties we want the machine learning model to have. We not always want them to be just like think or act like we do, but if they're useful or helpful in certain ways, then that's probably already good enough. Yeah, that's what I'll add.
Great. So I remember in the beginning, like most people here agree, like in a certain level, we do want to learn like physical dynamic from the data, or like you definitely need to use the data. And some of us propose like we probably want like a neural network or something to approximate the data. So a question from the audience, William. So William asked, like, do people have any thoughts on the danger or strategy of training on simulated data? If we want to make these algorithms practical for real world problems, is interpretability a necessary component for our models?
I'm happy to have someone else go first. I have something I could say. I mean, so certainly, well, first in particle physics, it's a place where the simulators, through decades and decades of building these simulators and adding a ridiculous amount of detail, they model the data at like incredible accuracy. And one thing that's very nice about them is you can intervene on the simulation. You can say, well, what would happen if like the power went out for this part of the detector, and you can simulate and see what the data would look like. And well, we know they have shortcomings. They're not perfect, but and it seems like maybe it's missing the point, but basically the strategy has just been keep working on making the realism of the simulators better and better. And if it doesn't match, figure out some way to add more flexibility so that it does start, like residuals essentially and things like that. And what's a little bit interesting to me is that when I've watched what's happening in robotics, I don't do robotics, but there's this whole sim to real picture and how it, total failure and everything. But, and I looked at those, at least early on, like the simulated environments look nothing like the real thing. They're like the little blue boxes, and they look like, like Pixar's movies from the 1990s or something like that. And it's like, well, no kidding, it's not going to work. I mean, I don't mean that disrespectfully. I just mean like my intuitive reaction as a physicist was like, you need to work a little harder on your simulation before you start expecting that thing to work. And what's also kind of interesting is that after putting a bunch of time into that, those approaches start to work better, right? And so, but there always are going to be, there are going to be shortcomings, but at some point, the gap between them is maybe not much different than what you would get from trying to learn data in one setting and domain adaptation to data in a different setting. And I think you learn a lot along the way because you have so much control over the simulator. So I think it's not the only solution. Physicists also figure out ways to use real world data, and so it's usually some kind of hybrid in the end. But yeah, I think you can get quite a bit out of working with simulated data, and it's also a place where maybe there's something to learn from a lot of scientists because the funny thing is I think a lot of scientists don't really have techniques and heuristics that they've developed over decades, and they have often very poor way of like formalizing what they're doing in a way that's transportable to the discussion that we're having here. Even though like really there's a lot of like clever ideas floating around in the different disciplines.
Yeah, anyone want to like add to it? Like how do we, if we want to use like a learned model for physics, then how can we make it like more robust or so it don't do crazy thing in the real world?
I feel like I have to say something in defense of computer graphics, who was responsible for those simulators that looks like Pixar movies in the 90s. And Niels can back me up. We're from the graphics community. I think you're certainly right, Kyle. The the simulators were invented a lot of in the 90s actually for video games, right? So we're you know, one thing that people are interested is just to blow things up, you know, like to generate this kind of unrealistic but spectacular scenes, and we deliver that. But you know, roboticists just kind of blindly took them and then started, you know, saying that they're going to train robots with that using, you know, deep reinforcement learning. So of course, you know, the first generation of the, you know, the policies hit the wall of centurial, or hit the gap, centurial gap, very quickly. And definitely true that, you know, in the last 5 years, we've seen a lot of advances, both in terms of having more robust policies, that are kind of less sensitive to the fidelity of the simulation, and also the simulator itself becomes better. And we're also very good at doing system identification. I think there is one missing. You have a good simulators, you have, you know, like robust or, you know, randomized policy training schemes, but you also need to have a very, very effective system identification procedures that can scale to a high dimensional space. So all these things kind of have to happen at the same time to make to cross the centurial gap.
Oh, Kyle, your hand is raised. I'm not sure whether you want to add. Oh, okay. Okay, cool. So people talk about, like, if we want to train like a learning-based model for the physics, then there are actually two kind of things that's kind of important. So one is the bias built into your model, and the other is the data you are going to train your model. So from the audience, Arijit asked, like, what do you think is the value of creating a data set that will allow us to learn like a good model, or we should put most of our efforts on building the models itself?
I actually feel that ideally the agents knows how to collect data themselves. I think that's the ideal word, right? So I think from Carl's presentation is that if you have an agent that learns like what is the next set of experiments to do, like kind of come up with hypothesis and come up with a way to collect those data, I think that is the most effective way of doing that. But I think that's probably like too idealistic. So maybe right now we kind of need to like start with some smartly created data, or have some kind of environment that allows the system to kind of explore for the initial experiments. Yeah.
Anyone want to add to the question? So either on how to make the model more robust, or spending effort building like an environment that will allow us to collect good data.
Just a quick comment on that. I think when you build that environment, that you already kind of you know, generate more bias, right? Like, what do you mean building an environment? That's a simulation itself, right? And then use that environment to collect the data, and then train another environment to predict that environment. It does, yeah. So I think we need the real world data. If this question has to make sense, I think that do we need a real world data set? And then I think the question is that how do we make it generalizable? How to make it, you know, it feels like it's going to be like case by case at the end. And
yeah, totally agree. Yeah. And also another thing kind of relevant to the environment or data we're using. So how do we evaluate like the physical understanding of a model, and what are possible tasks that will allows us to evaluate like fairly for all the models? And maybe one thing, like maybe asking this in a more psychological way, how do we test whether a system, when you propose the task, how do we test whether the system is really understanding the physics behind the task and not just solving the problems through shortcuts? Oh, Kelsey.
Yeah, I actually think this question is quite related to the previous question in like building environments. And I wanted to say something to that first, which is in some defense of like why it's potentially important still to consider how to make data sets or how to make environments, which is just like taking computer vision as a lesson, right? In that like they created these benchmarks like ImageNet that were extremely important for benchmarking progress and comparing different methods, right, for a goal that the community all agreed was important. And so I think that part of the problem in physics, and like something that's come up across many of the talks today, is that there isn't a single goal that we're all trying to work towards collectively. Like we each sort of, as Karen was just mentioning, like each different system is sort of potentially for a different purpose. And so we have to come up with particular ways of evaluating it that make sense for the particular purposes that we're trying to accomplish. And to that end, like a lot of what we have proposed is like the importance of being able to use physics, or one way of measuring it is to look at how systems can use that knowledge to like plan, like in robotics, right? As opposed to just predicting what will happen next. Because just being able to predict what will happen next, like, is not particularly useful if you wanted to deploy the system to like do different kinds of things. And to that end, I think that at least until the last couple of years, there was not nearly enough work on actually trying to make problems where you would really need to be able to generalize to a actually new problem that the similarities really only are physics, right? So a lot of what we've been doing is trying to create such environments where like the only thing you can learn across settings is physics, and like that's what will allow you to use like a frying pan for the first time to crush a fly instead of to fry an egg, right? Because you can understand sort of that a frying pan is heavy, it's probably good for crushing things, you can hold it in a particular way, etc. And so I think that this does, again, depend on the problems that you're most interested in, but my answer would be that we do need to think about how we want to measure things like generalization. That's very tied into how we build environments, and looking at generalization, I think, is perhaps the best way of trying to understand physical reasoning.
Wonderful. Maybe Tamar can go first. Not next.
Yeah, so somewhat boringly, I'm just in agreement with Kelsey. This is a yes and to what she was saying. I think particularly the emphasis on generalization. I'll mention two things briefly. One, and this is maybe a slight disagreement with Kelsey, while I agree that we need to focus on some kind of shared goal, I think ImageNet is actually a good example of the pitfalls, right? We say, okay, we all agree that this is what we need to do. We need to recognize cats and bats and dogs and things like that. And then we do that and we achieve 100% on it, or 99% or whatever it is. And then someone comes along with ObjectNet and says, actually, if you really understand cats, you should be able to understand cats when we rotate them, right? Now we're at 60%, right? There's a danger of like these systems that we think are doing X are not doing X. And there's a similar danger that would happen in physics. The solution to that is the one that Kelsey was mentioning, which is generalization. And she already pointed to some interesting work that she and others have been doing. There, I'll also mention just that we should probably, I'll make a case that we should take a lead from development, right? Cognitive development, in the sense that people there are asking similar questions. Here's a system, a baby. We don't exactly know what the baby is doing, or well, what the baby is thinking, right? What is their understanding? We think they're running some sort of program. They have some kind of expectations. And people are spending decades trying to prod this thing and understand what that expectation is. And exactly, you have these kind of arguments of like, well, maybe the baby really has an understanding of solidity, so let's do these two things. But maybe that's because I use my hands. I guess we should use these two objects. No, it's seen these two balls before. Let's use novel objects. Like, people have tried very carefully to come up with these kind of schemes to rule out low-level understandings. Now, the debate is ongoing there. It's definitely not settled in development, but I would recommend people who are interested in that, at least, to take a page from development.
Okay, great. Kyle, you can go next.
Yeah, no, it's great. I think I agree with both things that were said. I just add to a little bit. I mean, one is that this idea of planning and generalization, I think definitely one thing is, I guess, obvious, but the generalization that we're talking about is a richer form of generalization than what you often hear about in like deep learning. It's not like out of sample generalization, or even kind of like generalization to kind of a domain shift. It's really, it's a generalization across like totally different tasks, and so the way that you talk about it is a bit different. I will say that in my own journey, when I back up, 7 years or something, and I started first talking to a lot of deep learning people, there was a part where I look at, it's very easy to be critical of your own field, and then it's like, okay, well, look at us physicists, we're trying to communicate to some deep learning researchers about what is our task. We can't even articulate very clearly what our goal is. When we try to have these conversations, we're constantly sort of moving the goalposts. Like, this is our task, and they're like, okay, well, if that's the task, why don't you approach it this way? You're like, no, because the following set of reasons. And so it was very frustrating for our like statistics and computer science colleagues to engage with us. And so then we went to a period where it was like, okay, we have benchmark data challenges, very Kaggle type challenges, very clear goals, sort of ImageNet style. And then you started seeing engagement, but it was fairly shallow, I would say. Like, okay, you have the newest, deep learning model crushing some benchmark, but what are you really learning? And then in my own journey, I would say at some point I started to realize that, that if you look at how like physicists were designing things with a ton of heuristics where, for instance, we want to identify electrons in our detector, but they're going to be used in 15 different settings. And we don't optimize it with some kind of downstream goal in mind. We optimize it to understand how well do we understand like electrons, that kind of object, because it's going to be used in different contexts. And somehow the approach seems to work. We have made discoveries, we built complicated things, we learn about the world, but it's not in some kind of end-to-end objective optimization. It's really through all these intermediate points where we try to like check our understanding. And it's and I started to realize that actually it's really this kind of heuristic objective meta learning setup that is part of why it's successful. And it's kind of fascinating. I don't know. And I think that it's not an accident, that is happening for a reason. Yeah.
Yeah, sure. Go next.
Yeah, I want to add to it. I think it's great that to evaluate whether the model can understand physics through, or like the basic understanding of physics through generalization, through planning, and in particular for like a new task in robotics. But also, I think even if they can generalize to new tasks, it actually sometimes may not necessarily mean that they really understand physics. And the example I have in my mind is that for kids, like actually can do a lot of tasks, but they probably don't understand physics until they go to like high school, right? And then and for us, how we test whether they understand physics, we give them exams, and and then like. So equivalent is that can we examine our machine learning model? And then I started to feel like, why it's necessary to do those exams if they can do the downstream tasks really well? Isn't that enough? I think it's probably not enough when we consider using this kind of machine learning model to discover new things, like new physics laws or whatever things that we not yet understand, or new scenarios or new type of like physics or environment. Then I think that's when we really need them to understand the fundamental rules or physics or whatever the law that's governing all the visual observations. Yeah. So I think this is like a two different type of goals that depends on like what you care about. I think if you just care about the system works really well, then maybe like test them on generalization on downstream tasks probably enough. But if you care about like scientific discoveries, then ideally they can like kind of write down or summarize what they understand about the physics of the laws. Yeah.
Great. Niels?
Right. I wanted to come back to one other aspect of the question, the shortcuts. So hearing the question, I thought actually shortcuts can also be quite exciting. Of course, there's the undesirable, clearly unphysical, unwanted kind, but if there's some unknown, simple mode or so in the solution, it might be exciting to find out about it. And if I have a network that actually discovers this, that would be great. Then the problem becomes a bit, how can I check whether it's the unwanted kind or the interesting kind? And I think generalization is definitely a good and important way to evaluate that. I think also a bit more the traditional simulation debugging style of trying to figure out what the intermediate states are, and then trying to dig into, say, activations of different layers and mapping them to the physical quantities that come out in the end, and basically procedures like that potentially help to distinguish what the model is actually learning. But it's a tough and interesting direction.
Oh, Tomer. Yeah.
Yeah, if I may just briefly follow up on something that Sharon said, that is not quite the question, but I'm glad that we ended up here in the debate space. And it's good because we've been agreeing too much on this panel. So here's a point of disagreement. Specifically to the point about, oh, children don't understand physics. It's only when they get to high school that they understand physics. And that's what we should focus on, this kind of verbalizable understanding. I think it's important to point out that that's not the target for a lot of intuitive physics, right? And in the same way, to put it, this is a bit of a silly example, but in the same way that we think like convolution, kids don't understand convolution. Surely neural networks of visual recognition are probably at around age 20. I mean, that's when my college kids understand convolution. Like, no, right? We think that there's a lot of things that your brain is doing that you don't have conscious access to, all kinds of complicated things that these networks and brain systems can be implementing. And I think intuitive physics can be quite complicated and sophisticated and understand dynamics and objects and all kinds of stuff about solidity and approximations without kids or adults being able to verbalize it necessarily, but should be a target for our common sense reasoning systems.
Great. So we are very close to the end of the whole workshop, but I just want to end this session with the last question. So the last question is, what do you think is the most important problem that need to be solved in order to get this general and generalizable physical reasoning? So for example, for other researcher, what would you want them to put the effort in it?
I hate dead space. So well, I will say that there was something that Kelsey mentioned, which I think I had something similar, but this ability, this kind of multi-fidelity, intuitive physics or different types of simulators and world models at different scales that are with different kind of computational budgets and accuracy, speed trade-offs, and being able to find kind of different, coarse-grained approximations of whatever, so that for the task at hand, you can figure out kind of which model should you use for trying to do some kind of quick reasoning, and then to some level understanding how those different models like relate to each other. That seems to me just more and more like absolutely key to the way that I do science, and something that when I think about if I wanted to algorithmically do something, that's what I would need to make things be tractable. And it seems like it's within kind of like there's ideas floating around for how to do that, but we're certainly not good at it currently.
Tom.
I'm not unique in saying this at all, but again, focusing on intuitive physics and people and things like that, I think a central open question. There are two kind of questions for why we don't already just go down the route of de-rendering the image and then building something like a simulation and then running that simulation forward. Again, if we're not aiming for NASA level de-rendering, why aren't we doing that just now and having machines with common sense reasoning, right, for intuitive physics? Turns out de-rendering is really hard, but I expect that'll, we'll make significant advances on that with people that have been on this panel and otherwise in the next 6 years. But the thing that is maybe much harder, and I think some people are working on, but I hope a lot more people will be working on, is in these tasks, we ask people things like, do you think this will fall? Do you think this will break? Where do you think this will go? Things like that. And implicit in that is the connection between language and intuitive physics, or rather abstractions and intuitive physics, right? What do you mean by fall? The physics engine, if it perfectly de-rendered the tower into something like Zelda Breath of the Wild, doesn't contain fall. It contains the objects are over here, now they're over here, now they're over here, now they're over here. A grad student needs to go in and say, oh, fall means X% of the blocks is below height H, I guess, right? I decided. And that turns out to work pretty well in capturing what people are saying. But we don't have a system that can then go from the word fall to interacting with the physics engine and do that successfully with things like fail and catch and glorp and smash and all these other things that we use very naturally. And people are working on this, absolutely, but it's a much bigger challenge and something that I think we'll have to solve in order to get intuitive physics off the ground in the full sense.
Sharon.
Yeah, I have a silly answer. I think okay, it's very easy to say that you guys should work on the field that I work on, but actually the opposite. I think that's it would be great if people can develop better simulators. So people working in graphics, please go ahead and make it better, because I feel it's so fundamental for so many things that we do. Like, I think if you have a better simulators, we can use that to collect training data. We have better simulators. We can do better planning on it. We can do like de-rendering. We can do like forward dynamics. So I think, yeah, better simulators is what I really want. I think that's kind of like a silly, but it's like very fundamental for many things that I do today. Yeah.
Yeah, that's just endless requests, right? You want it to be accurate, you want it to be fast, you want it to be stable, now you want it to be differentiable. No, I'm joking. I think that's really it's great for I mean, not just computer graphics, right? Because right now, you know, you hear the talks from today and other workshops, you know, differentiable physics, differentiable rendering, all these things require you know, expertise beyond just computer graphics, but, you know, computer vision and machine learning and all that. So it's really exciting to see, and robotics, of course.
Nelson and Kelsey, do you guys want to like mention something like interesting direction that you think people should work on?
Sure. I'll just say that, I mean, obviously, given what Kyle said, yeah, I'm quite interested in the space of like meta representations, or like meta learning how to trade off representations. And in particular, if I want to be more specific within that, I think that something that we still don't have a great grasp of, or still don't do super well in learning physics, is learning like multiple levels of abstraction. And this is something like, I was trained as a physicist, and you learn about like Newtonian mechanics, and then you learn about quantum, and you learn about gravity, and these are like very different scales at which things operate, right? Or even in just statistical mechanics, like you can describe the motion of individual atoms, or you can describe like heat equations, right? And they're all representational choices that we make to answer different kinds of questions that involve different kinds of approximations. And I think that like we really don't have good mechanisms that can learn essentially to make the right approximations to answer different kinds of queries. And I think that doing that is like a critical thing, not just to being able to do interesting stuff within science, within physics, but also something that people do all the time that we really don't have like super great explanations for yet.
I quickly wanted to add on to one point that Karen mentioned. What I think is also super important is to keep on working on working across and communicating across disciplines. I think there's so many tough problems, and it's still surprisingly difficult to work with people from different fields and to bring all the great ideas together. So I think that's actually also a good point that still needs a lot of work to have everyone help out.
Great. I think we're pretty much out of time. So that's thanks all the panelists for this intriguing discussion. It's very interesting to gather people from different fields together and then to talk about their opinions on these like super critical questions.